All right. Are there any questions before we get started? We're back in nomenclature. We're going to try to get, I would ideally like to get all the way through chapter 4 today. It'll help with your, I think you have a cyclohexane lab this afternoon. So I'd like to get through that at least initially so that you have some background before you go to lab this afternoon. Okay, there are no questions. We'll get into, oh, let me get that light off so it doesn't. There we go. I'm gonna turn it off. There we go. Okay, so in this slide, or this information is asking you to find the longest carbon chain. Okay, and the reason this one is on there is that you're going to sometimes find that there are chains that are the same length, but you see differences in the way that the groups coming off the chain, or the substituents, are illustrated. So, for example, if you come up on this side, we'll do one over here. The longest carbon chain, these are identical obviously, is 7 carbons. So hopefully you found a 7 carbon chain. And it is, let's see, this one. Okay, this is one option to get a 7 carbon parent. Okay. Now on this side, you can find a 7 carbon parent by coming down like this and then over. And if you had gone up here, that would have been fine too, because this is 1 carbon, this is 1 carbon. Okay, but on this one, you also get a 7 carbon parent. Okay. So now we have to decide which of these two is the better chain before we start to determine the numbers. Okay, so when you look at what's highlighted in blue here, coming off every carbon that is inside those squiggly blue lines, those carbon atoms here, 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 this one here, those are in the parent chain. These things off here are the substituents. So this is a substituent, and this is a substituent. Now on this 7 carbon chain, you have a substituent here, a substituent here, and a substituent here. Okay. So on this side, you get 2 substituents. This side, you have 3 substituents. So which one is better? Okay, well then you have to look at the kind of substituent that you have. Okay, so this substituent coming off here that has 2 carbons in it, this is a chain. Okay, so this is a chain substituent. This substituent has a center carbon and then branches. So this is called branched. Over here, you have a chain. It's just a 1 carbon chain, but it's just a line. A 2 carbon chain here, and a 2 carbon chain up here. Okay, so the rule is that you always pick the parent chain with the higher number of simple substituents. And the chain is simpler than a branch. Okay. So even though this only has 2 substituents, it has a branched. This has 3. So this one over here, this is going to be the parent chain that we pick. Okay. Right. Are there any questions about that before I erase the left-hand side of this screen with the branch substituent? Okay. All right, so I'm gonna take this off. Okay. All right. Now what we have to do is take this molecule, and I'm going to redraw it and then erase. Like that. Okay. And now we have to number it. And we're going to start here and come down to here, and then reverse. Start here and go up to there. So 1, 2, 3, 4, 5, 6, 7. If we go back up, 1, 2, 3, 4, 5, 6, 7. All right. So then we compare our number schemes, and in the red, our first substituent is at 4, 5, and 6. Our green numbers, the substituents, are at 2, 3, and 4. Okay. 2, 3, and 4 are a lower set of numbers than 4, 5, and 6. So the green numbers are correct.
I do have a question.
Yes.
So when you're circling the substituents for the green path that we just did, would you say 1 is a substituent 2, or just 2 because it's the chain?
Say that again. So you're talking about down here?
Yeah, the green one, would that be counted as a substituent?
No, that's in the parent.
Oh, okay.
The only way it could be a substituent is if instead of counting that as carbon 1, you had counted this as carbon 1. Because these are equivalent. This is a CH3 group. And this is a CH3 group. So once you get to, once you're at carbon 2, you could either come up here for carbon 1 or come down here for carbon 1. It wouldn't matter. You would still have something coming off carbon 2. You see what I'm saying? Like if this is 1, you would say there's a carbon here, and then a substituent. Or carbon 1, carbon 2, substituent. So the pathways are the same in that case. Does that make sense?
Yeah.
Okay. All right, so I'm going to take this side off. Okay. All right, so now we have our numbers, and we know that we have a 7 carbon parent. And the only thing we have on here is carbon-carbon single bonds. Okay, so this is an alkane. So the prefix for 7 is hept. So the parent is a heptane. So this means 7 carbons single bonded together. Okay. Right. Now what we have to do is we have to identify these groups as substituents that are coming off of the chain. Okay. So I'm going to erase this one, these, so it's a little cleaner. Okay, so over here on substituent 2, you have a 1 carbon substituent. Okay. Off of carbon 3, this carbon is in the parent. This carbon and this carbon are in the substituent. So parent carbon, 2 carbons in the substituent. Okay. And off of carbon 4, this one is in the chain. These 2 are in the substituent. So this is also a 2 carbon substituent. Okay. Now I want you to write a note. Substituents do not exist separate from a molecule. Okay, so this group up here, our 1 carbon substituent, it's just a CH3. Okay, CH3 isn't a molecule because a CH3 only has carbon making 3 bonds. So this bond is required for this thing to exist. So you can't just have a CH3 floating around. The prefix names for substituents are the same as the prefix names for carbon chains to turn the parent. So if you had a 7 carbon substituent, you would still use HEPT, hept. But since it's not separate from the molecule and it has no identity on its own, you use the prefix name, then you use the ending YL. So 1 carbon prefix is meth. Since this 1 carbon group isn't a molecule, but a piece or a branch off of a molecule, it's called a methyl group. Okay, so methyl is not the same thing as methane. Methane looks like this. This is an independent molecule. That's methane. Methyl is a piece off of a larger molecule. Okay. 2 carbon substituents, the 2 carbon prefix is F. So ETH, then a YL. There's 1 carbon here, 2 carbons. This is also an ethyl. Okay. Now we have to name it as 1 continual chain. When you list your substituents in the name, you list your substituents alphabetically, not by number. So even though methyl is on carbon 2 and you have ethyls on 3 and 4, since E is earlier in the alphabet than M, the ethyl groups get named first. Okay. But I can't just say I have 2 ethyls. I have to give the number where they are. So I have an ethyl group, we're using the green numbers, on carbon 3 and on carbon 4. Okay. So I write 3, 4. Because I have 1 of them on 3, 1 of them on 4. If I have 2 numbers, I have to use di. If I had 3, tri, 4, tetra, So I have 3,4 diethyl. So 2 ethyl groups, 1 on 3, 1 on 4. 2 methyl heptane. Okay. All right. Questions?
Will we ever be asked, like, given the name and then asked to draw the molecule?
Well, your exams are going to be all multiple choice. So it would be given a name, which of the following molecules matches. So you should be able to go from structure to name, name to structure.
Okay, thank you.
Okay. Now, in that regard, if you have to go from the name to pick a structure, the easiest thing to do, I would start out here, heptane. But I wouldn't draw mine as a squiggle because I think that, I mean, you get free rotation, so it's eventually going to take on this alignment. But I would just draw 2, 3, 4, 5, 6, 7. Put a methyl group on 2, an ethyl group on 3, an ethyl group on 4. So this is the same orientation. This is the same molecule as this. It's just this one's a little bit easier because the parent chain is shown left to right. In this one, the parent chain squiggles. But yes, you should be able to go back and forth. Are there any other questions before we add in halogen substituents?
Yes, I have one question.
Sure, Hannah.
I understand like the 3, 4, and the 2. Why is the 1 there? That maybe this is a dumb question, but
The 1. Where do you see a 1?
in the 3, 4 diethyl. Oh, that's an L.
That's an L. Yeah, sorry. Okay. So take this off. Any other questions? Okay. Now, if you have the slides, the next one is already drawn for you. Yeah, I think so. Okay. All right. Now, in this one, I drew it in the easier way. So the longest chain is right to left. Okay. But you still should take the time to number in both directions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then go in the opposite direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. The red numbers are 4, 5, 7. The green numbers 4, 6, 7. Okay. Now, when you compare the numbers, you compare the first number of the red to the first number of the green. And in this case, they're the same. So the first number isn't going to distinguish the red. Oh, here comes my cat. Sorry. Loki, go on. Go on, baby. The first number isn't going to distinguish red from green. So you have to then go to the second number. Okay. And since 5 is less than 6, this is the better numbering scheme. Okay, so you just move on into the numbers until you find the pair that separate one path from the other. Right. Then we come back and we look at our substituents. So on carbon 4, this carbon here, that one is in the chain, in the parent. It's only these out here that are in the substituent. So we have a 2-carbon group here, which is an ethyl group. Okay, and again, this carbon that's going to be a black dot, that one is in the parent. So you can't double count them. They're either in the parent or they're in the chain or in the branch coming off. So in the parent, and then 1, 2, 3. So 3 carbons is prop, so propyl. Okay. And then on carbon 7, you have a chlorine, but when it's on an alkane, you call it a chloro. Okay, so if you have your halogens on your molecule, that would be fluoro. Don't add an L there, not FL, that's Florida. F, fluoro, chloro, bromo, and then the one that's weird, it's weird to write and it's weird to say, it's called iodo. Right, then you write it as one continual chain in alphabetical order. So A, B, C, this one would come first. 7 chloro. Then E, 4 ethyl. 5 propyl. Decane. Okay, and I want you to do one on your own. Okay. And work on this one and try to get the numbering scheme for that, like a name written out for that molecule. And then we'll do a couple more that are just like weird practice ones just to show you a couple different varieties. Okay. So this one, always start with the longest chain, which again is left to right. 1, 2, 3, 4, 5. 6, 7. Oh, I did that wrong. Let me put that 5 up in here. 1, 2, 3, 4. Ooh, this is going to be interesting. 5, 6, 7. Okay. I didn't plan that to be like that. Wait, no, it's okay. That's okay. So the red numbers are 3, 4. The green numbers, oh, this is fine. 4, 5. Okay. So of those two, the red numbers are right. Chloro and alpha carbon 4, you have a 1 carbon, so it's methyl. C comes before M. 3 chloro, 4 methyl heptane. Questions about that one? Okay. Now the next two are just to sort of show you a couple of different things that might happen and when you're naming. Okay, so here's one. Okay. Okay, it's number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so with the green numbers, you get a substituent at 3. With the red numbers, the substituent is at 4. So the green numbers are better, but you have 2 substituents on the same carbon. So carbon 3 has a methyl group and a methyl group. Okay, you have to name both of them. So it looks weird, but you would say that on carbon 3 and on carbon 3, you have 2 methyls on a hexane parent. Right. Now the last one, let me see what's next. No, I've got I've got a couple things left to do on naming. Okay. Oh no, on your slide it says. Okay. All right. Number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Now this time when you write out the numbers, you get the same numbers in both directions. So in this case, the numbers can't discriminate or distinguish which pathway is better. In that case, then you're going to have to use the alphabet to determine the order. So this is a chloro, and C in the alphabet comes before E. So in this case, when the numbers can't be used, you can use the alphabet. So the chloro, since it comes first in the alphabet, that would get the 3. like that. So on this one, if the locant numbers do not indicate the correct path, use the alphabet to pick.
I have a question.
Sure.
What would you do in the case if like that was an aromatic? Like, how would you count it if there was an aromatic in the structure?
So when you have if you look in your textbook, you have your functional groups, right? So you have alkane, which is then it goes alkene, then it goes alkyne, and they go in a list and they have a number associated with them. Actually, they don't. So then the next one is alcohol and then ether. So the order that they're given tells you the priority of which family is more important. The lower down on the list, the higher the priority the functional group is. So if you had a compound like this, you would say that this is an alkene because it has a double bond. It's not an alkane with a double bond coming off of it. The whole molecule then is an alkene. So if you have an aromatic ring, you would name it as an arene. So if you had so you have an ethyl group on an arene. So this isn't a aromatic, this is an aromatic ring with a alkane substituent. It's not an alkane parent with an aromatic substituent. So this one would be called ethylbenzene. Does that make sense? So you have to, and the way it's going to work is like we're going to learn how to name alkenes first. Then we're going to learn how to name alkenes. Then we're going to learn how to name alkynes. Alcohols are easy because you just add OL. So this one, 2 carbons is eth. So this is ethanol. So you get the OL ending. Those are, to me, they're just as easy as any of the others. But these are the ones you're going to learn how to name in 211. And then when you get into the next semester, that's when you learn how to name the other ones. Because the naming rules, like the book, it's called, there's a group called IUPAC. So it's the International Union of Pure and Applied Chemistry. They make the rules on how we name molecules. And then the rules are a gigantic book to the point where if your molecule is so complex, you just draw the molecule in a computer program and the computer program tells you what the name is. Because it knows all the different priorities. Does that help, Benjamin?
Yeah, thank you.
Okay. All right. So I'm happy to give you, do you guys want another, can you go down to the participants and do a vote, please, on whether you want a practice one or should we move on? Ooh, it's tied. I like watching these come in. It's kind of entertaining. Still tied. Oops. Oh. All right, it's about half and half. So I'm gonna go ahead and put one up. If you don't want to practice, you don't have to. Oh, it's pouring at my house. Okay. Oh, I'm gonna make it fancy. Put that up there. Okay. Let's work on that, and then we'll move on. Okay, now this one, I hope I drew so that you have to turn a corner, but I can't promise. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Yes. Okay, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so your first number with the red sequence is a 2. The first number with the green sequence is a 4. So the red sequence is better. F gives you fluoro. These are 2 carbons, so that's ethyl. E comes before F. 4 ethyl, 2 fluoro, heptane. The next thing we're going to do is look if there aren't any questions about linear systems to name versus rings. Okay, and not aromatic rings, just carbon rings. So this is just hexane. So a 6-carbon alkane, which would follow CnH2n plus 2, C6H14. Okay. Now, if you instead have a 6-membered ring, when you count the number of hydrogens, because each of these carbons in the ring is already making 2 bonds, all of the carbons in this ring only need 2 hydrogens. So it becomes CnH2n, C6H12. Okay. So when they're linear, they're saturated. all the carbons are full with the maximum number of hydrogens possible based on the number of carbons. This molecule does not follow this mathematic rule. So this compound is not saturated, so you call that unsaturated. And we'll talk more about that in chapter 15. Okay, so these aren't the same compound because they have different numbers of hydrogens, but they have the same number of carbons and they have all carbon and hydrogen single bonds. So this is all carbon-carbon single bonds, carbon to hydrogen single bonds. Same thing here. So to name these separate, the rings separate from the chain or the chains, is you just write cyclo in front of it. So this is cyclohexane. Okay, now there are a few naming issues with rings that are different than with chains. Okay. So I'm going to just draw the molecules, and then if you don't believe me about the name, then you can do the numbers later on. Okay. So if you have a substituent on a chain, one substituent, it doesn't matter if there's one or two, if it's on a chain, this substituent needs a locant. So this would have to be written as 3-chlorohexane. Okay. If you have one substituent on a ring, you don't need a number. This is automatically carbon 1. So this one you would just call chloro, oops. Cyclohexane. Oops, I'm gonna run out of room. Okay. If you have more than two, then they need to have a number. And you would start at one of the carbons that has a substituent. So it's either 1, 2, 3, or 1, 2, 3. Okay, if you go around in this direction, you're going to end up with a 1 and a 4. No, wait, a 1 and a 5, excuse me. So 1 and 3 is lower than 1 and 4. But since it's 1, 2, 3, 1, 2, 3, then you would use the alphabet. So this would then have to be labeled 1-bromo, 3-chloro, cyclohexane. All right, the last part about rings before we move on into some of the branch substituents you need to know the names of. I'm just going to draw a simple ring, a 4-membered ring. Okay. All right. But what I want you to consider is that rings are, and I'll explain this more in a little bit, just write kind of. They're kind of flat. They're not perfectly flat because the rings are going to shift to alleviate stress. Right? But rings have a top side and they have a bottom side. Okay. And so you can use dash and wedges, those indications of the bonds, dash and wedge bonds, to show relative placement of the substituents. So I'm going to take this compound. This right here, it doesn't show you whether the bromine and the chlorine are on the same side or on different sides. So you don't have anything to indicate besides the name. But if the ring had been drawn like this is saying it's coming up, the chlorine is coming up, and the bromine is coming up. So they're on the same side. So those two are given a relationship called cis. So you would add that to the name, cis 1-bromo 3-chloro-cyclohexane. If they're on opposite faces, one is a dash and one is a wedge, then they're called trans. So trans 1-bromo 3-chloro-cyclohexane. Okay, so only if they're indicated by dashes and wedges do you have to include cis and trans. If they're not shown on dashes and wedges, you don't. Are there any questions about the rings? I know I'm going kind of quick through this, but naming is one of those things that if you don't practice it on your own, you're not going to learn it. You could watch me do it for hours, and it's just going to be something that you pick up on your own time when you practice. Okay, the next two slides are about different types of, some different names that have stuck around through the literature of branched groups off of parent chains. Okay, so I'm going to draw the parent just as a box. Okay, and so this, and then I'm going to have a parent over here as a box. Okay, and these are going to be the 3 carbon substituents. So off of the parent, your 3 carbon substituent could look like this: 1, 2, 3. Okay. Or your substituent could look like this: 1, 2, 3. So it's either coming out as a chain or it's coming off as a branch. Okay. If it's coming off as a chain, it's called propyl. If it's coming off as a branch, it's called isopropyl. When you use these names in alphabetizing, the P is used in propyl and the I is used in isopropyl. If you have 4 carbon substituents off of the parent, you end up with more combinations. Okay. So on this one, you need to write 4 boxes of parent, parent, parent. Right. Right. You could come off 1, 2, 3, 4. Okay. You could come off like this: 1, 2, 3, 4. One, 2, 3, 4. All right, and the last one, 1, 2, 3, 4. Okay, now these are flashcard things that you're just going to have to sort of learn, memorize. Okay, this one is the chain for carbon, that's called butyl. Now this one, you have the point of attachment from the parent to the carbon is in the middle of the chain. This carbon, which is the point of attachment, I'm going to kind of try to circle it, is attached to 2 different carbons in the chain. So this carbon within this 4-carbon chain has 2 groups attached to it. So it's called a second butyl for secondary. Now this one has like a Y shape similar to this one. This is called isobutyl. Okay. This one is named similar to how this one is. So you have this carbon here in your branch substituent that's bonded to 1, 2, 3 carbons. So this is considered tertiary butyl. Okay. So the way that if it looks like a Y shape, it's iso. This to me looks like a chicken's foot. So that's how I keep this one separate from these 2. If it's a Y shaped, it's iso. Chicken foot, tertiary butyl, or tertiary group. Okay, now the only thing about this set that's annoying is in the naming. Okay, the B is used to alphabetize. The B is used to alphabetize. The B is used to alphabetize, but in isobutyl, you use the I. Okay. The reason that is sec and tersh, these prefixes refer to numbers, and numbers aren't used to alphabetize. Iso is an old name to discriminate the bonding pattern, so it's part of the actual name. It's not related to a number. So this carbon, like I said, is bonded to 1 carbon, 2 carbons, so that is secondary. This carbon, 1, 2, 3, tertiary. And like I said, I would flashcard all 6 of these. Are there questions about those? I always feel like I have to apologize for this slide because it's kind of annoying, but it is important. And in the book, they go into the different options for the 5 carbons. You don't need to know those. You need to know these for 3 and these for 4. Okay. So the next slide is talking about constitutional isomers, which we've already talked about when we did the isopropanol versus 1-propanol versus methyl ethyl ether on the first day of class. But these are just carbon chains. So if you don't have the slides in front of you, you could just watch this and it would be fine. So that's a 6-carbon group. All of these have the same formula, C6H14. Okay, oops, I do have room for one more. Okay. So these are all constitutional isomers of C6H14. Okay, so constitutional isomers, remember, are different ways of connecting the same formula of atoms. Okay. Because of free rotation, it's not obvious that this isomer is identical to this one. Okay, the only way that you would be able to tell if these were the same would be to name them. And in both cases, you would get 3-methylpentane. That's what this one is. 3-methylpentane. Okay. As the number of carbon atoms increases, the number of constitutional isomers increases rapidly. Okay, so for example, C6H14 has 5 constitutional isomers. Let's see, 10H22, so just increasing by 4 carbons, you end up with 75 isomers. Okay. So I can promise you that I'm never ever going to ask you to draw all the isomers of a compound, because I don't want to try to find 75 different things. Okay, so just if your textbook is asking you to draw all the isomers and you get like, I don't know, 6 out of 10, you're fine. Don't worry. All right, the next slide, the next part of this is just to talk about some properties of alkanes. And we have discussed this in the past. Alkanes as a family, they're kind of boring, to be honest with you. They don't do a lot. So alkanes as a family, especially if they're not if they have halogens on them, they become a little bit more important. But these are just CnH2n+2 as a family, and the cyclohexane type things. So these have limited affinity for other molecules, because alkanes are nonpolar, so they can only interact with other molecules through London dispersion forces. Okay. They're pretty much inert, which means they don't react with other reagents, which makes them excellent solvents. But you need to be about 4 carbons, 5 carbons, 6 carbons to get liquids. The smaller alkanes like methane and ethane and propane are gases. Okay. They all are good fuels. They burn well. For the most part, they're non-biologically active or relevant. They don't participate in many things. The only thing that they do that's chemically interesting, we're going to come back to in chapter 11. Okay. Alkanes do react with halogens, so fluorine, chlorine, bromine. You wouldn't use fluorine because fluorine's horrible. It's just really violent reactions. So they participate in reactions with halogens through what's called a radical pathway. Okay, and a radical is something that has a lone electron. So not a pair, but like if you drew this, 1, 2, 3, 4, 5, 6, 7. So this electron over here is all by itself. So that would be called a chlorine radical. Okay. In order for this reaction to occur, you need light. And you need light at a very specific wavelength in order to create the first set of radicals. Don't worry about this one until we get to chapter 11. Okay, now the next part of this is we're going to get into using the model kits. All right, and so I have my molecules built. So if you don't have your molecule built, that's okay. You can always rewatch this video with your molecules. And so we're going to look at three of the molecules, 3 alkanes in a new perspective. And this is section 4.6 in your book, and it's called Newman projections. Okay. So the molecule we're going to look at first is ethane. So if you drew it as a line bond drawing, that's all you would get, is a line. Okay. So just for a little bit of clarity, we're going to write it like this, okay, as a Lewis structure. Remembering that both of these carbons are sp3 hybridized, so these bond angles are 109.5 because these are all tetrahedrals. The 2 carbons are tetrahedrals. Okay. So the way I have the molecule drawn right now is sort of like this. Okay, so you can see so the black carbons are the black balls, these are the carbon atoms. And the only reason why these hydrogens are different colors is so that you can tell the hydrogens from one carbon here separate from the carbons over here. And I picked yellow and green because I'm a Green Bay Packer fan. Okay, so this is what I got. Now, to draw a Newman projection, what we're going to have to do is take this molecule and rotate it on so that it's sitting on the 4 carbon, sorry, the 3 hydrogen atoms. Right? And I'm going to, my camera's not quite perfect. So I'm going to tilt my molecule up so that the carbons overlap one another. So these are the hydrogens in the front. This is the carbon in the front. Then there's a carbon in the back, hydrogens in the back. So when you look down this carbon-carbon bond, you see the relative spatial placement of these hydrogen atoms in green relative to those hydrogen atoms in yellow. And when you draw this orientation, it's called a Newman projection. Okay. Oh, let me just, so I'm going to try to, it's not quite right because of the camera, okay, but this is fine. All right, so you draw a circle with a dot in the middle. Okay. The dot is the carbon in the front. The circle is the carbon in the back. Okay. I'm going to draw another one so I can add the hydrogens. Okay, so now if you look at this molecule orientation, the front carbon is the dot, and it's attached to these green hydrogen atoms. Hydrogen, hydrogen, hydrogen. Okay. Then on the back one, this circle, they're coming off like this. Okay. So this is the Newman projection of turning ethane on the side so that you can see the carbons overlapping. This angle, which goes from hydrogen to carbon to carbon to hydrogen. It's here and it's here. It's called a dihedral angle. Okay, and we're going to look at dihedral angles that are either 0 degrees or 60 degrees. As it's drawn right now, these are all 60 degrees. Okay. All right. I'm going to leave that down here for right now. Okay, and then I'm going to take this molecule. So I still have my greens in the front. This bond right here, this carbon-carbon single bond, I can rotate the carbons relative to one another. So one of the carbons I'm rotating clockwise, the other carbon I'm rotating counterclockwise. Okay, when I look at the Newman projection though, there's one. If I rotate, they overlap. So that's a dihedral angle of 0. Rotate to 60, rotate to 0. 60, 0. They're staggered or they line up. Stagger, line up. Okay, so those are my two options. Okay. So here's one of the Newman projections. This is called staggered. And it's called a conformation. So a staggered conformation. When they line up, you think about what happens, what do you call it when you have the moon overlapping the sun and people go nuts and go outside and look at it and burn their eyeballs out? Okay, when they line up, it's called eclipsed. And that's eclipse conformation. Neither of these is 0 energy. You can't have 0 energy. You just have low energy. You have high energy. Okay. Right. This dihedral angle is 60 degrees. This dihedral angle is 0 degrees. The difference in energy is due to this interaction where you have bonds that overlap in space. Okay. Are you good so far? Are there any questions?
I have a question. How can that be in your eclipse? You said that's 0 degrees.
Uh-huh. Yeah.
What plane is that on or whatever?
Okay, so if
Maybe
you
I'm
look
not
at it like this, a dihedral angle has 4 components. So it has this molecule, this one, this one, this one. So these 4 that my fingers are touching. When they're eclipsed, they line up. So there's 0 degrees between this carbon to hydrogen bond and this carbon to hydrogen. Carbon to hydrogen directly overlaps carbon to hydrogen.
Okay, you're just overlaying those 2 planes then. Okay.
Yeah, overlapping those 2 planes. Exactly.
Okay, makes sense.
Just gotta look for the right word here. My brain just froze. Okay. So when you have these bonds that overlap in space, it's called torsional strain. Okay. And that's going to result from electrons in one bond overlapping electrons in a second bond. Okay, so the electrons in this bond are negative, and they're close here through this 0-degree angle. So the strain is going to be between these two bonds. Okay. As you rotate around that carbon-carbon bond, what you end up seeing is like an energy difference like that goes like this. Low, high, low, high, low, high. So this would be staggered, eclipsed, staggered, eclipsed, staggered, eclipsed. You can't stop this free rotation from happening. There's enough ambient energy at room temperature and pressure for this to occur. Are there any questions about ethane before we add another carbon and look at propane? Okay. Erase this. Okay. Now propane is like that. Okay. We can only ever look at down one bond at a time. So we have to look down like carbon 1 to carbon 2. Okay. All right, so here's propane in the zigzag like this. So the two carbons that have green hydrogens on them, those are going to be the carbons that are going to be in the Newman projection. This carbon with the yellow hydrogens, that's going to not be represented by a circle or a dot. Okay, so we're going to turn this, and I'm going to have to organize it a little bit. We're going to turn this so that the two hydrogens, sorry, the two carbons that have green hydrogens stack. Okay, and so you can see that on the back carbon down here, you have a methyl group coming out. Okay, this is still staggered, and you still can rotate, eclipsed, staggered, eclipsed, staggered. Okay, so when we draw these two, or this Newman projection, there's carbon 1 and carbon 2. So carbon 1 had only hydrogens. Carbon 2 had a hydrogen, and a methyl. And I'm going to draw this with some space. Right? Staggered. Okay. And then eclipsed. Okay. Oops. Okay. 60-degree dihedral angle, 0-degree dihedral angle. Okay. The staggered is low energy. The eclipsed is high energy. Okay. Now, in this case, when you have a carbon, you have another substituent. When you have these things, so here it is, staggered. Okay. Now it's eclipsed. Okay. So you still have the bonds overlapping. So you would have torsional strain here, here, and here. So again, torsional strain is what happens when you have to overlap bonds in space. But now what I want to do is I'm going to turn this to the side, okay, and see how close these hydrogens are. So this hydrogen has an electron cloud. This hydrogen has an electron cloud, and those electron clouds are going to interact. They're both negative, so that's going to be a repulsion when these two hydrogens are too close to one another. So when you have two groups like this, even a hydrogen being as small as it is, when you force them to share space, you call it steric strain. So this interaction is going to be a higher energy interaction because it's torsional and steric versus this one that's just torsional strain. Just torsional strain. But still low energy, high energy. You don't have to know the numbers, like how much the strain is worth, but you'd have low, high, low, high, low, high as you went from staggered to eclipsed, staggered to eclipsed. Okay. Are there any questions about propane before we look at butane?
I have a question.
Yes.
If you were comparing just the energy of torsional strain and steric strain to each other, which one would be higher in energy?
It's going to depend, the steric strain is going to depend on the size of the group.
Okay.
So if you had like, so hydrogen is really small. Let's say, for example, that you had an iodine here. Iodine is huge. So the iodine is going to be, the iodine to methyl steric strain would be higher than hydrogen to methyl steric strain. But the torsional strain is just 2 electrons in a bond overlapping 2 electrons in a bond. So you might see slight differences, but you're really going to see more differences in energy based on the sizes of the group that are competing for space. Did that answer your question, Karen?
Yeah, thank you.
Yep. Any other questions before we move on? Okay, if you don't have a model kit, I am hoping that today's lecture is showing you that you should have one. They're very fun to play with, and there's always somebody who needs one, so you can, they're pretty easy to resell later on. I had my first one for like way many more years than I'm going to admit to, but I just got a new one and I love it. Okay, so let's move on to butane. Okay, so 4 carbons is butane. Now this time what we're going to do is we're going to look at this bond between carbon 2 and carbon 3. Okay. So here's the butane. Oh, there. So it matches the diagram. So we're going to be looking down the bond from this carbon here to this carbon here. So the only hydrogens that are going to be on the Newman projection are going to be the ones on these green ones. Okay. So we'd have to kind of move it like this so that these are in the same plane and then turn it. Okay. So this is carbon 1 with the red, 2, 3, oops, 4. Okay. All right. So staggered eclipsed, staggered. You can already see what's happening. Eclipse. Look at how close, I mean, they're touching. Staggered, eclipsed, back to staggered. Okay. So we have several Newman projections that we can write. Okay, this was the first one that we had. Where the methyl group on carbon 3 is opposite the methyl group on carbon 4. Okay. So this is staggered, but in anti-conformation because the two methyl groups are as far away as possible. Then we rotate by 60 degrees. Oops. And you get to a staggered conformation. Right? Sorry, eclipsed. You rotate again. Okay. Staggered. But now this one, it's staggered, but these methyl groups that are shown with red and yellow, they're so big that even though the dihedral angle is 60 degrees, they're still interacting. They're still bumping into one another. Okay, so this staggered conformation does not have the same energy as this staggered conformation. Okay? This staggered conformation has a component of steric strain from these two groups being close. Okay, it's called a gauche interaction, G-A-U-C-H-E. So this is staggered but anti. This is staggered but gauche. And then you would rotate again by 60 degrees. And then you would have your methyl groups eclipsed together. Now, it's really hard to tell. You'd need the numbers to know that a methyl-methyl interaction by steric strain is higher in energy than two different hydrogen to methyl steric strains. But what you do need to know is that this is low, this is higher, and then the eclipsed are always going to be highest. Now, in this one, this interaction with the steric strain from the two methyl groups is costs more energy than this one. But with, like I said, without numbers, you would not need to know that. But eclipsed is always higher in energy than staggered. But staggered with gauche interaction is higher in energy than staggered with anti-conformation. So this would be lowest, higher, and then highest. Okay. So torsional strain, torsional strain, torsional strain, steric and steric. Over here, torsional, 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 and a whole lot of steric strain. You would have steric strain here. This is the only time where in staggered conditions you can get steric strain, but it's given that weird word gauche. Are there any questions about the Newman conformations for ethane, propane, or butane? Okay, again, those are things that take some practice. Okay, so what we're moving now into is section 4.9, which is cyclohexane or cycloalkanes. Okay. You need to have at least 3 carbons in order to get a ring. And they follow the standard geometric shapes. So this would be cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane. Okay. Now, rings were essentially considered to be flat, but they're not. So the rings, the only one that's flat is cyclopropane. The rings are going to, it's called pucker. They either pucker or bend themselves out of the plane to reduce torsional strain, steric strain, and what's called angle strain. Okay, now what angle strain is strain in a ring when the ring angles deviate from 109.5 degrees, because all of the carbons in these rings are sp3 hybridized. Okay. So if you look at cyclopropane, this angle is 60 degrees inside an equilateral triangle. It's 90 degrees inside a square. So 60 deviates from 109.5 significantly. So this is a highly strained ring. Okay, the bonds are actually bent like bananas. Cyclopropane is highly reactive, trying to alleviate and open up the ring to get these carbons back closer to this 109.5 degree angle strain. Okay, how you measure the strain is that you take your ring, which is a hydrocarbon, and you burn it in oxygen, and you make carbon dioxide, water, and heat. And this heat is a measure of the strain. So in the interest of time, we're going to skip the slide that shows you like the small 3, 4, and 5 membered rings puckering out of the plane. And we're just going to go straight to cyclohexane, because cyclohexane is the most important biologically relevant ring. And it puckers and bends out of plane so that these angles are 109.5 degrees. They don't look like they could be, but they are when the ring is out of plane. Okay. So if we just look at the ring on its own, here, does anybody need the information on this slide? I'm gonna erase it so you can see my ring. Yeah. All right, so this is a 6-membered ring. And if I tip it on its side, you can see how it's puckered out of the plane. It still has like a plane, but they kind of zigzag up and down around the ring. Okay. Now you can draw Newman projections of it, and there's one in the notes, but you won't be asked to draw those. They're kind of hard to draw and see. Okay. So before I add some hydrogens on here, I want you to look at this cyclohexane ring, and I want you to think about it like a chair. Okay. So this carbon here where my hands is. So if you go to the dentist, they make you sit in this chair, and you're very sad. I hate going to the dentist. Okay, so this carbon is where my head goes. This area down here, this is where the booty goes. And then your knees bend and your feet are here. Okay. And the remarkable thing about a dentist chair is that they can move it. And they can put your feet up. And these cyclohexane rings will do the same thing. The feet can come up and the head can go down by rotating around those bonds. And what you end up with is a slightly different chair. So up, down, you get a chair, up. Oh, sorry, so aggressive. Okay, so let's see, up, down. Okay, so these are called chair conformations of the cyclohexane ring. Okay, this one has to come down, up. Okay, when you do a chair flip, you go through a conformation that looks sort of like this. Looks like a boat, and it can twist, and you can get a twist boat. But the lowest energy conformation is the chair. Okay. So we have to be able to draw a chair. And the way you do that is you start with a set of parallel lines going up towards the upper right-hand corner. So they either go in this, we're going to start in this direction with our outside bonds. So 2 parallel lines pointing towards the upper right. Come down and come back up, but don't have these points overlapping. Draw it down and then draw it up and connect. Okay, so the head would go here, your booty, your knees, your feet. Okay. In order to go to the other, the other chair, we do what's called a ring flip. Okay, so this is chair 1, and we ring flip and we get chair 2, not chain, chair 2. Okay. To get chair 2, this carbon here comes down. This carbon here goes up. But when you draw the other chair, instead of going to the upper right, you're going to have to go to the upper left. Like that. Now, most people draw one chair really well and the other chair not so well. Okay, start with your parallel lines. Make it a bow tie sort of thing, but don't line up. It looks like a Budweiser label if you're over 21. This one does. Looks like a Budweiser label. Okay. This carbon that was in red is this carbon down here. This one in green is this one up here. Okay. And when you go around the ring, you have to keep the carbon numbers or identification's the same. So if this is A, carbon B, C, D, E, and F, this is A, B, C, D, E, and F. If you go in this way, like clockwise, to identify the carbons, then over here you have to go clockwise. Okay, so I went in this direction, A to B to C, A to B to C. Now, when you have groups on your rings, I'm only going to do a couple just because of I don't have a ton of colors. You have positions along the ring. Okay. So I'm going to erase these and just draw one big carbon or one big cyclohexane. Okay. Now, off of each of those carbons in the ring, you have 2 hydrogens. Okay. So one set is shown in red and the other set is shown in yellow. Okay. So you have, if you look at these 2 carbons are overlapping now, so you're essentially seeing a Newman projection. Okay. Off of each carbon, you have a hydrogen that comes straight up and a hydrogen that comes straight down on the neighbor. So one up, if this one is up, then the next one over is straight down. Okay, so if you have a peak, you go up. If you have a valley, you come down. You can't draw really anything inside the ring, like pointing in. Okay. Up, down, up, down, up, down. Okay, alternating around the ring. So this is an up carbon. So I have an up, down, up, down, up, down. Okay. When they're straight up or straight down, they're called axial because they're parallel to the axis of the ring. So if you drew a line through this ring, and you said that was the axis, like the Earth's axis, about which the molecule could spin, those hydrogens are parallel, so they're axial. Okay. Now, if you look at the yellow ones, they're coming out from the ring, but they're coming out across from the central line around the ring. So the central line around the Earth is called the equator. So we call them equatorial positions. Okay. If your axial is up, then your equatorial position is down. If your axial position comes straight down, your equatorial position comes up. So axial down is with equatorial up. Equatorial down is with axial up. And it's all the way around the ring. Okay. This is axial down, equatorial up. Axial up, equatorial down. Axial down, equatorial up, axial up, equatorial down. Okay, none of my equatorial positions can be inside the ring. They all have to radiate out from the ring. I need about 5 more minutes. Are there any questions about the difference between axial positions and equatorial positions on a ring? All right, let's look at what happens to those positions when we flip. All right, so here's axial up, axial down, equatorial down, equatorial up. Okay. The green carbons are the ones that I'm going to have to move in order to make this chair flip. So this one down here with the A is this one up here, A. This one here, which would be D, is here. Okay, so then if this is E, this is E in here. Okay. Before we draw it, it's easier to see on the model. So here's one of my chairs. Okay, and the reds are axial up. Now when I go to the next ring flip, oops, I broke it again. Now look at what happened to the positions. Now the hydrogens that had been axial are now equatorial, and the yellows that were equatorial are now axial. So when I draw that, so hydrogen, carbon D is this one right here. So now my red is up and the blue is down. And then I move over to carbon E. Blue is up and axial, red is down. So if you look at this hydrogen here, is this hydrogen here. So during the ring flip, axial becomes equatorial. Equatorial becomes axial. But this is axial up. This is equatorial, but up. So up stays up. Down stays down. But axial becomes equatorial. Equatorial becomes axial. So the relative placement up and down doesn't change, but the axial and the equatorial does. So this is a good place to stop. There's about 5 or 6 slides left from this chapter, and it's talking about what happens with these rings when you have non-hydrogen atoms. So that might be something that's covered in lab today, but we'll finish this material tomorrow, and then we're going to move on into chapter 15. Tomorrow, what day is it today? Wednesday? Yeah. Okay, that's good because chapter 15 is the last chapter that'll be tested on Monday. Are there any questions today before we stop? It's a lot to take in, I know. Okay, well, I will put this video up as soon as I get it from Zoom, and I will see you guys then, yeah, I'll see you tomorrow in lecture. All right. Okay, everybody, have a good rest of your day, and I will talk to you soon. You're welcome. Have a good one.